Our next lecturer will be Alina Deac from HZDR. And although you've already learned a lot about spin torque, spin transfer torque, SOT, but I believe that Alina will give you a more thorough, overview of the spin transfer effects, not just for switching, but also the high frequency dynamics. So let us welcome Alina.
Hello, can you hear me? Should I drop them? Okay, so I've seen your poster, so maybe what I'm going to show you is going to be a little bit too fundamental for you. I think this is maybe more of a historical perspective on how things got to where they are nowadays. So maybe you still learn something. Yeah. So the entire universe told me I should have stayed at home. So be patient with me so I don't die when you read it. Right. So I guess the first thing I should tell you is that I'm in the Hello Zentrum Dresden-Rossendorf, which claims to be in Dresden in Germany, but it's actually not. It's somewhere in the woods because it was a former nuclear research center and it had to be in the woods, so it was 1 bus per hour. Welcome to civilization. These are all the people who somehow contributed to the data that I'm going to show you. Is mostly my own data because, when you have a sample and you know your sample, then that's what you know best. So I'm going to first talk about giant magnetoresistance and spin transfer, because I was once giving a talk in a seminar and somebody asked me why does the current get spin polarized when it goes through a magnet. And I had realized that I got so used to just knowing that I forgot the actual reason why this was happening. And just as a warning, as you grow older, the worst questions you can get are always from people who have no idea what they're talking about. So they are going to ask you fundamental questions that you have grown accustomed to accept for granted, and then you're going to be like, oh, I used to know this, but, huh? So, yeah, be aware. Anyway, then we're going to talk about switching and secession. So, here's the giant magnetoresistance. So do you know, how many of you know why the current gets spin polarized? I see 1, 2, 3. Well, the thing is, the general assumption is that you get scattering of the electrons. So in the general two current model is so you get the spin up and spin down currents who do not intermix mostly. And so if you have scattering for some reason or another, you can only scatter spin up into another spin up state, and you can scatter spin down into another spin down state, but you cannot interchange. The room temperature does not actually really true, but okay, this is the general. So the thing with materials, oops, materials like cobalt, iron, and so on, you have the spin up E-band, which is completely filled. So, and then you have the spin down E-band, which is only partially filled. So the spin down have a higher probability of scattering because they have a value of the states up here while the spin up don't. So that means that most of the current gets carried through the spin up because they get less scattering. So, am I right? The three guys who said, you know. So this means that if you have a material like copper, which is obviously not magnetic, and then you have random spin orientations for the electron. And then if they then encounter a magnetic material like a cobalt layer or something, then the current will get spin polarized, and most of the electrons that come out of this when the electrons flow from the left to the right are going to be pointing up. So if you then add another layer here, which can be pointing up or down, or in any other random direction, you can basically decompose these spins into up and down because any random angle is a combination of up and down. So the down electrons at this interface are going to have a higher probability of scattering back, and also they're going to have a lower transmissivity through the layer. So basically, this means that depending on how this layer is oriented, the current is going to see a higher or a lower resistance. And this means that the relative orientation of the two layers determines the resistance of the system, and this is effectively GMR. And GMR was a big thing in its day, which is now a long time ago. Basically, the discovery of GMR enabled all of the progress of hard disk drive and so on. And actually, I have a question for you. Do you know what a hard disk drive is? Because about 10 years ago, so nowadays our things have SSD. So about 10 years ago, I almost died when one of my PhD students said he doesn't know what a hard disk drive is. Yeah. Anyway, so going on this reasoning, do you know why hard disk drives are still important?
Because that's where most of the stuff in the cloud is stored, right?
Yes.
Yeah.
Good work. Thank you. You made me feel younger. Okay. So, yeah. So, okay, going back to the GMI, you know, so like the low, the spin-up electrons in one layer, if the two layers are parallel, are going to be still spin up in the second layer, and the spin down is going to be spin down, and then you can build this resistance obviously you get different resistance circuits for the parallel and anti-parallel state, and something in between. So generally, this means that the resistance of your layer is going to depend on the magnetic configuration. And so you can, if your layers are asymmetric, you can use a magnetic field to switch from the parallel to the parallel state, and then you can measure magnetic resistance curve, which looks like this, and you can identify the two resistance levels for the two states. It's really easy, earth-shattering. So, okay, this picture here is from 2010, because this one, my student said he doesn't know what a hard disk drive is, so I stopped counting. So essentially the importance of the GMR discovery was that it enabled the development of hard disk drives. And just so you know, because I didn't, this was the very first hard disk drive that was developed by IBM, and you can still see it because they have it in California. And this whole thing was stored a total of 5 megahertz. So just like a picture. And yeah, nowadays, you know what's in your phone. Now what spin transfer is, and I'm only talking about classical spin transfer, so I'm not talking about spin orbit torques, I'm not talking about other things. It's basically the inverse effect to GMR. So in the GMR, the electrical bias you measure across a tri-layer system depends on the orientation of the two layers. And in stream transfer, you can change the orientation of the two layers by applying an electrical bias. So it's just the inverse phenomenon. So these two things go hand in hand. So now if you have the same stack as you had before, as the electrons go from left to the right, they will get spin polarized in the first layer, and then they will come out of this layer with most of the electrons having their spin around this orientation. And then at this interface there are several things that happen. So the reflection and the transmission coefficient of the spin have different probabilities. So that means that if you decompose this spin into a sum of spin up and spin down, the spin down has a higher probability of reflection, and spin up has a higher probability of transmission. And that means that when you recompose the spin of the electrons in this layer, they will basically have a different polarization rate. And also, as they enter this layer, because they are at an angle with respect to its magnetization, they will start precessing around the magnetic going to lose angular momentum. This angular momentum must go somewhere, and it goes into manipulating the magnetic state of the free layer. So I think you all know this, but I will bore into this explaining. So you can generally explain the dynamic state of the free layer by using the Van-der-Waals-Hilbert equation, and this gives you a precession term, whereas if you have an applied field which is not collinear with the magnetization, the magnetization is going to persist around the local field and is going to go on forever if you don't have losses. But in a field system, just like friction, you do have losses, and used by the magnetic damping, and this will slow down the precession. And then if you add the current flowing through the thing, then you're going to have another term here, which is a damping-like term. So this means that you can use this term to basically cancel or overcome the damping. Now, if this term is larger than the damping term, then you can induce switching. If you just about compensate it, then you have steady state precession. And basically these were the first experimental demonstration of forces. So okay. So this is a very old sample which I had as a PhD student, and which Albert Ferter told me I should stop trying to understand because it's too complicated. But I didn't have any other samples, so basically I was stuck to it. So effectively what you have to look at is mostly this step. So these were cobalt iron layers which were laminated with like 3 angstrom of copper. And this was the point of this, was to increase the resistance of these 2 layers. And this was a GMR sample, so this is the copper layer in between the 2 of them. And this layer was basically a soft, which was exchange bias. And do you know why it's important to increase the resistance of these 2 layers in such a step? Nobody. So, because this layer is exchange bias, there's a antiferromagnet, which is the iridium manganese in this case. And if this is a GMR stack, the resistivity of the iridium manganese is basically 1 order of magnitude larger than the rest. So if you have a tunnel junction, you don't have this problem. But if you have a GMR stack, you do have this problem. So anyway, this was the stack that we had. And basically the transfer was to measure magnetoresistance curve, where you know you go from parallel to anti-parallel state, and then do a current sweep and identify these two resistance states at zero current as the same in this, and this was the proof that you've actually changed between the same two resistances. Now, again, because this is a GMR stack, we also have heating, and this gives you this curvature here. So this is asymmetric because you don't only have Joule heating, your stack is asymmetric, so you have Joule heating, and depending on the polarity of the currents, you also have Peltier heating or cooling, and that's why the curvature of this thing is offset. And there were actually later on proposals on how to use this Peltier effect for spin transfer. So then, if you want to prove that the thing is actually magnetic, because in the very first days there were people who thought they saw spin transfer switching, and then they were applying like 1 Tesla magnetic field, and nothing changed in the current. Is to see that this actually changes with the applied magnetic field. And so here you see different curves that increase in negative fields. In this case, the negative field favors the parallel state. So what you see is that basically, as you increase the magnetic field, the sampler tends to in the parallel state for a longer range of current. And this means that it's changing with the field, it's a magnetic effect. You can also see that the two transitions between the parallel and anti-parallel state are moving with different speed. So at some point, you know, so you have this hysteretic switching, which you need for a magnetic memory device, because it has to store the information when the field is not applied any longer. But then the two change, because the two transition move at different speeds, then at some point the transition will become reversible, and then you finally cannot apply enough field any longer to switch between the two states with the applied current. I mean, you can try to apply more current, but your sample is going to die. This was my only sample. And you can see the same effect if you measure magnetoresistance curves. So these are now resistance versus field at different applied current, and you can see that the effect is the same. So basically, the curve, this current is supposed to favor the anti-parallel state, and then as you increase the current, the sample stays in the anti-parallel state on a longer range of field, and then eventually it becomes reversible, and it goes into this kind of slanted reversal, which actually corresponds to precession. Okay, so then you can plot so-called phase diagram. I'm not sure who started to call this a phase diagram, because it's not a phase diagram, it's a state diagram. But somebody started it, and now it's called a phase diagram. So you can plot it by basically plotting the spot where the transitions occur, or if they are hysteretic, or the beginning and the end of the transition if the transition is reversible. So you can do this by using the current versus, the resistance versus current field measurements, or the resistance versus field measurements at different current. And you get exactly the same limits. So basically what this tells you and how you should read this is that let's say you start in the anti-parallel state and you do resistance versus current measurement, right? So if you start in the anti-parallel state, here, down here, you're going to stay in the anti-parallel state for as long as the anti-parallel state is allowed. And when this is no longer allowed, you're going to switch to the parallel state. And then if you scan the current back, you're going to start in the parallel state, sit in the parallel state until the parallel state is not allowed, and then switch to the anti-parallel state. And so you have these areas which are anti-parallel state, parallel state, and this bistability area where it's where you want your memory to function. And then you have these gray areas over here which correspond to these reversible transitions where neither state is allowed. And basically that's where you get precision. Now a different way of plotting this is by plotting the the magnetoresistance curve in this colorful plot where you plot basically the resistance you measure versus the current and field, and you get the same kind of bistability area, and then we have these areas over here where neither state is allowed, and where you get this reversible transition. So going back to modeling, the way you can understand this stability areas is by taking the Landau-Lefschetz-Gilbert equation and then basically solving it for dm dt equals 0. So this will only give you the stability of one specific state, parallel or anti-parallel. It will not tell you what happens in between. So if you do this and you take all the fields that are parallel, that are present in the system, then you will end up with effectively these lines which match pretty well what you get experimentally. So you can understand this in a intuitive way if you think that as long as either the current or the field are higher than the switching current or the switching field, you basically go into a given state. When the current switching current and the switching field, but they were opposite states. The sample goes into these gray areas over here, not green areas over here, where you basically get steady state precision. So one other thing you can see is that basically the slopes of these two critical lines are different for the two states. This is basically because in a GMR side, the critical currents from switching to the anti-parallel to the parallel state are about twice higher than from switching from the parallel to the anti-parallel state. This is effectively a consequence of GMR. If you measure a tunnel junction and you plot it versus current, which many people do, you will see the same thing, but it's from a different reason. So if you measure versus current, so in the current junction, the relevant parameter is actually the voltage, not the current, and the anti-parallel, the resistance of the anti-parallel state is a very high bias voltage dependence, and the resistance of the parallel state is basically constant. So when you measure them and you convert it into the relevant parameter, which is voltage, you don't see the same effect. But if you plot it versus current, you do. So this is a very old picture. I think this was from yeah, yeah. So I think this was from the creation of SpinTech, the first patent they had on this. I think the first patent they had. So effectively, what this just tells you is that you need to have hysteretic switching so that the information you store is actually stored. And then the problem at the time was to use tunnel junctions, and this has been solved by now, and I should know because they are all in Dresden, some in Singapore. And you need to, the current density is always a problem. And you need to keep the thermal stability reasonable. So the funny thing with the thermal stability is that they actually started off by requiring thermal stability for 10 years, and then it turned out that this was not feasible, so they downloaded the thermal stability to 5. So, but you get now in the magnetic tunnel junction is 5 years. Okay, so this is one of the first measurements on tunnel junction, and you can see whether exactly the same effects that we saw in GMR step. And for decreasing the switching current, the solution, and decreasing the switching currents and keeping the thermal stability at the same time is proved to be a problem because historically this was started off with in-plane structures, and in the in-plane structure the term that gives you the switching current basically is the demagnetizing factor, which is at least one order of magnitude larger than the anisotropy unknown. And so because technology made some progress, and then we started to be able to produce perpendicular magnetic layers also in tunnel junctions. This was the better compromise, because here you have the demagnetizing factor which plays against the anisotropy field, which is perpendicular. So this can be, so in this case, this is usually of the order of 10,000 Rashted, but the difference of these two can be much lower. So that's why the switching currents are lower in perpendicular. And yeah, you can now play this game. Now tunnel junctions with perpendicular anisotropy. So thermal stability depends